Hopefully you've had an opportunity by now to finish through question letter D and to check your answers to the table to ensure that you have approximately the same numbers that you see here on the screen. You're welcome to pause the video and zoom in on this so that you can see my numbers, but I tried my best to just kind of round each value to dollars and cents, since after all we're talking about money, and some of the decimals started to get a little unwieldy by the time you got to Friday, Saturday, and Sunday's values. Now in question letter E, it's asking an interesting question about some vocabulary that we almost may have taken for granted up to this point. It says, why is this pattern not arithmetic, even though we were adding numbers to generate each value in the table? And that's a really good point. We always think of arithmetic as adding, and yet this pattern can't be arithmetic. If you look carefully, the definition of arithmetic that hopefully you'll start to think about as you look at your numbers is that arithmetic sequences grow by the same adder each time. So if from Monday to Tuesday it grew by $100, a true arithmetic sequence would keep growing by 100 and 100 and 100, and that's not true here. The sequence grew by 100, but then it grew by 110, and then it grew by another amount, and then another amount. So it's not arithmetic because we're not growing by a consistent dollar amount each day. And for something to be truly arithmetic, its adder has to be consistent through the entire problem. So naturally, if it's not arithmetic, our brain probably naturally switches gears to the antonym of arithmetic, so to speak, the geometric possibility. So if it's not arithmetic, let's ponder, could it be geometric? Now geometric would mean that there's a multiplier, that times 1,000 gives you 1,100, and times 1,100 gives you 1,210, and times 1,210 gives you 1,331. And it's pretty clear that these are not nice numbers, so any potential multiplier would have to be kind of a weird looking number, but I'm not necessarily sure if such a multiplier exists. And if you can't tell just by looking at it, one option that you can consider is to pick any pair of numbers in the table, let's say 1,000 and 1,100, and to divide them. Because in theory, if 1,000 times something is 1,100, then 1,100 divided by that thing should be 1,000. And I can inverse that by saying, well, 1,100 divided by 1,000 would be 1.1. So let me just check that as a multiplier. If that works, then 1,000 times 1.1, yep, is 1,100. Okay, so I have a multiplier that connects the first 2 days in the jackpot table, but what about the next 2 days? Is the multiplier consistent? 1,100 times 1.1 is 1,210. So things are looking encouraging. If I try this again, 1,210 times 1.1, 1,331. It looks like, because the first time could be a fluke, the second time we're feeling pretty lucky, by the third time we're feeling pretty convinced, it looks like we do indeed have a multiplier. It wasn't an obvious multiplier, but it looks like we do have a multiplier of 1.1. And sure enough, you can keep checking this, and it gives you all of the same numbers that you would have gotten by doing the calculations your way. So we know now for sure that this pattern is geometric. So in letter F, could it be geometric? Yes, we have confirmed. You can explain or show in your own words how we confirmed, how we got that 1.1, but now we know the multiplier is definitely 1.1. So let's make a note of that to ourselves. The multiplier is definitely 1.1. Because letter G wants us to write an equation, and we know for an equation of a geometric sequence, we need to have a specific structure in mind. The geometric equation that we've always written, and this came from your notes from the previous packet, the Unit 7 packet, is T of n equals the initial value, whatever that is, times the multiplier, whatever that is, to the power of n. So that's always the equation structure that we need to use for a geometric sequence. Let's plug in these values that we know from the question now that we know them. T of n equals the initial value, or the initial jackpot, was given to us as 1,000, times the multiplier we just found was 1.1 to the power of n. So in question letter H, It says the first lotto winner finally picks the winning numbers on the 4th Monday of the month. And you can tell that's going to give us a lot of time to let this thing grow. So naturally the question becomes, well, what's the easiest way to figure this out? Do I want to keep extending the table to the next value? Because like if I go to day 7, I know now I can do this a little faster than I was doing it before. I can just multiply by 1.1. So day 7 I can get by doing 1771.56 times 1.1. But then I'm going to think about this question and say, oh, the 4th Monday. I mean, if this was the 1st Monday, day 7 would be the 2nd Monday. And then I think, oh gosh, that's a whole nother week till you get to the 3rd Monday. And then a whole nother week till you get to the 4th Monday. That to me sounds like it's going to be a lot of multiplying by 1.1. And while it's certainly efficient to multiply instead of doing it the way we did in letter B, I don't know if that sounds all that appealing. I mean, to be honest, extending the table for another 2 full weeks sounds really crazy. So let's perhaps consider the fact that we have an equation, and that's one of the benefits of an equation, is to think about these kind of shortcuts that we can take using our algebra skills. If I think about a little calendar here, I have our Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday, which I know is not how a traditional calendar is laid out, but bear with me here. The first Monday of the month was kind of our initial value here. So when I think about that first Monday, I'll write n equals 0. Because technically, that was the value in the table that I was first starting with. N equals 0 was the first Monday. So that means Tuesday was n equals 1, Wednesday 2, Thursday 3, Friday 4, Saturday 5, Sunday 6. So the second Monday of the month must be n equals 7. And of course you can keep numbering if you want to, just so you can keep track of the days, but hopefully by now you picked up on a pattern. That the third Monday of the month would be n equals 14, and that the fourth Monday of the month, the one in question, is n equals 21. So now we can say to ourselves, oh, okay, hold on. If I know the n value, and if I have an equation with an input spot for n, why can't I just plug in my n into that spot? That's the benefit of having an equation, is that it saves you from having to do that repeated multiplication. Remember what would happen if you plugged in 1,000 times 1.1 to the power of 21? This kind of resembles the multiplications that you'd be doing. If you were doing this the long way in the table, you'd be doing 1.1 times 1.1 times 1.1 times 1.1 21 times. So writing it in equation form saves you that hassle of doing 21 calculations, and now we can simply do this. 1,000 times 1.1 to the power of 21, which gives us about $7,400 by the time it's all said and done. Now, of course, you can round your answer however you'd like. Usually I recommend that you round your answer to dollars and cents, because that, of course, is what the problem is referring to. So I would probably write my answer as 7,400.25. Now, you can round down. The rounding isn't really that important right now. You can even round to the whole number, 7,400, totally your choice. But the idea here is to figure out first that there were 21 days that had elapsed in the table, and that you could use that 21 in the equation rather than with repeated multiplication. Now, if you can think about something strategic, I'm going to pose a challenge to you, an independent challenge, but something I'll follow up with in the next video. Is there an easier way that you could have figured out that the multiplier was 1.1 without having done all of the calculations from letters A through E? Like, it took us a while to get to the point where we realized that the multiplier was 1.1. I mean, we had to have the table, or so it seems. Can you think of a way that we could have gotten 1.1 from the original text of the question without having to do all this work? I'm going to pose that as a challenge to you. I'm going to see if you can come up with an idea. If you can't come up with anything, then in the next video I'll explain another way you can get the 1.1 without doing all of this work. But I want you to see if you can discover it for yourself. So between now and the time you start the next video, try to think, without peeking at the key, How could you have predicted that the multiplier was going to be 1.1 without having done any calculations?